So hi everyone, my name is Anas, and in this quick demo I'll be going over the PageRank, the web crawler, and the database schemas for our search engine for assignment 1. So starting with the crawler, I have the crawler.js file open over here, and you'll see that we're using the crawler node.js package. Well, with some customized logic. So for example, we have max connections here set to 10, and that basically ensures that we crawl concurrently without overwhelming the server. Our entry points for crawling also depend on the dataset, obviously. So for the fruits dataset, we seed the crawler at the n-0 HTML page, and for our personal dataset, we're looking at the node.js.org documentation site over here. So like when the crawler downloads a page, we extract the title, and we extract all of the p tags, the paragraph tags. So like we then sweep through all the paragraph tags, extracting the raw text, which we then sanitize by converting it to lowercase and splitting this extracted text into an array of alphanumeric words. Like this is really an important array because it forms the basis of our term frequency scoring that we'll compute later on. And next, like the crawler finds all the anchor tags to discover the outgoing links. Like a big challenge here we found was normalization, so I used Node's built-in URL module to parse every link and strip away hash fragments so that we're not visiting the same page over and over again just because it has different anchor links. I also implemented like strict domain filtering, so for the personal data set, any link that was leaving the nodejs.org domain, we just ended up discarding. So now looking at the database persistence, which is a little down here. So here we have the database operations, right? And as pages are processed, we need some way to store them. So for that, we chose MongoDB for our database because it's a document-based database, and that perfectly like fits the fact that we have arrays of words and links, which is kind of like an unstructured type of data. And like for each page crawled, we perform an extraction to save its title, any outgoing links, and the array of extracted words. But since like we also need to build the reverse graph for PageRank, I extract just the unique outgoing links from the page, and for every target URL, I push the current URL into its incoming links array. And like because this could involve like dozens of database calls per page, I grouped these updates into an array of promises, and we execute them concurrently using the promise.all. Next, looking at the page rank and content scoring logic. So we have the page rank .js file over here. And so like once the crawler finishes, the database is populated obviously, but we still need to rank the pages. And so attempting to compute the page rank on the fly or querying the database for every link traversal was going to be very slow. So instead, the script pulls all the pages for a dataset into memory and builds like an adjacency list. And this adjacency list maps exactly which nodes link to which other nodes and pre-computes the out degree for every page. We initialize every page's rank to 1.0, and then we enter a convergence loop with a damping factor of 0.85. And that represents the probability that a user continues to click links. In each iteration, a node's new page rank is calculated as the sum of the page rank of all its incoming links divided by their respective out degrees. So like we repeat this process until the maximum change across all the across like the entire graph drops below the threshold that we selected to be 0.0001. And for our node.js dataset, we found that this usually converges well within our 50 iteration limit. So once that's done, we batch update the final scores back to MongoDB. And like finally, like how is this used, right? So if I open server.js over here, scroll down. So yeah, like when a search query comes in, the server calculates a base content score by simply counting how many times the user's search terms appear in a page's crawled word array. And if the user requests a page rank boost, we multiply that base term frequency score by the page's pre-computed page rank. And we found that this content relevance with structural authority pushes the best results to the top. So to wrap up, we found that separating the system into like these three distinct phases of crawling, ranking, and serving was like one of the important design decisions that we made, and it allowed each component to be optimized for a specific task. So heavy operations like parsing HTML and resolving graph structures happen completely offline and asynchronously, leaving the server free to respond to search queries like almost instantly. So yeah, that's everything.
Hello, I'm Trista, and I build the RESTful server for this assignment. So let me just start off by showing the endpoints. I'll first show off the fruits A endpoint. So in this example, where I have here, I have a query of apple, go set to false, and a limit of 10. So if I were to copy this, go into my browser, and then paste that into here, so we see that we get 10 results according to the limit, and that we have the URL, score, title, page rank, and a server URL, which is the URL relative to our server. And right now the score is a flat number because it's not affected by the page rank. If I were to go into the parameters in our URL and change from false to true, you can see that the score is now affected by the page rank and change accordingly. So that is fruit A. Next, I'll show the personal endpoint. For the personal endpoint, we chose the Node.js documentation site. So in this example, the URL, I am doing a query with the term node, no boosting, and a limit of 5. So if I format this, we can see that we have 5 results according to the limit, and we have the same formatting as we saw in fruits A. And then going back into the parameters here, if I were to attempt to change the limit from 5 to something insane like 10,000, we see that we don't actually get 10,000 results. Our limit is hard set to 50, so this is actually just 50 results instead of 10,000. Alternatively, if someone were to input an invalid number such as -5, we can't have -5 results. So when we enter this, we still get results. We don't get -5 results. We actually get 10 results because if the number is invalid, our server defaults to 10. In a similar vein, if we were to get rid of this limit parameter altogether, I'll just delete that, we see that we still get results and the server defaults to a limit of 10 if we don't set that limit ourselves. So that is it for the personal endpoint. Next is the page endpoint, which is the page details for all the URLs that we have. So this will work for any of these server URLs we have in the browser here right now. So I'm just gonna copy the first one I see, go into here, and we see it's just a page, and we just specify the URL. So if I enter that, you see that we get the details for that page in our database. So we have the URL, the title, the incoming links, outgoing links, page rank, and then the word frequency based on how many times the word appears in the contents. So that is it for the 3 endpoints. All right, so for the RESTful design, there are 3 parts to it. I'll start off with the client-server separation. As you can see in the code, there is no reliance on any client or any front end. So the only thing that the server cares about is processing the data and then returning it in the proper response format. So in this case, it doesn't matter if the client is a web browser or a command line tool. The only thing the server does is process the data and then return it accordingly. And whatever the client does with the data is not the server's business. Next is the statelessness of the server. As you see that every request is independent, there is no use of sessions or logging in or anything in order to do every request. The only thing that matters is the parameters in the URI. As you can see here, the only thing that matters is the query return that we want, whether or not we want it to be boosted, and what the limit should be. So next is the HTTP methods we use. So as you see here, we can see we use get methods here, and we also use HTTP standard codes depending on what's happening in the server. So for example, if we can't find a page, then we'll just send out a 404 error. If there's any internal server errors, we send out a 500 error. And then if we get the correct results and we can return them neatly, we send out a 200 response code, which is all the HTTP standard codes. Next, I'll talk about the content score calculation. You can see the function for it is down here. It's a very simple calculation. It's just a term frequency calculator. So we have the query, and sometimes the query can be split into multiple queries. So for example, the query here is just apple, but down here it's apple, banana, and grape. So in this instance, this will be split into 3 separate terms. And then it just goes to the content of the page, and then it just sees how many times a certain term is in the content. So for example, in here, if the content only had apple 3 times, then the content score would be 3. If this content here had apple 3 times, banana 2 times, and the grape 1 time, the score would be 6 in total. And then if there's no content or there's no query, then the score is a flat zero because nothing to score. And that is the standard score. If the person decides that they want to boost the score, then we will multiply the content score that we calculated and then multiply that by the page rank that we also calculated. So that's it for the content score calculation. Next is about the engine scalability and improvements. So right now our search engine is efficient as we saw in my demo. We only have a few hundred pages to go through for each data set. So so right now the way the search works is that we load all the pages that we have for a certain data set, calculate the content score for every single page, and then we sort these out based on the score and then return the amount of results we need depending on the limit. So right now this is efficient as is for our current size of datasets. We also use asynchronous calls, which means that the server can handle multiple requests at once. However, this kind of falters if we want to try adding more pages to our dataset. So if we want to have like 1 million pages, this fails very quickly because that means we'll be loading 1 million pages into memory, then we'll be going through every single page and calculating content score for every single page, which is not very efficient at all. So if we want to scale this up to be a bigger search engine, we would have to start looking into indexing or using a library like Elasticsearch, which means that the server will not be calculating the content score by like within itself. It would be stored in the database directly, which would be a lot more efficient in terms of data retrieval. Yeah, that is it for me. Thank you.
Hey everyone, I'm Jason and I built the browser-based client, which is the front end that sits on top of the API that Trista built. I'll walk you through the interface, demo both searches, talk about our personal site choice, and then finally I'll wrap up with a few critique points. As you can see here, the web app is a single page application. There are no page reloads anywhere. There is a sidebar with two tabs, fruit search and personal search, and clicking between them would swap the active section without touching the server. Another thing is that the active tab gets a blue highlight so that the user always knows where they are. And this whole thing is plain HTML, CSS, and vanilla JavaScript with no frameworks. Layout is a flexbox sidebar plus content pattern. And the detail view uses a CSS grid to show incoming and outgoing links side by side, which you will see in a minute. So here, let's go to fruit search and type in or search up apple banana and then click search. And then let's check off the boost by PageRank as well. So you can see that each section has three controls: a query field, a limit input capped at 50, and a PageRank boost checkbox. Heading search will trigger the doSearch function in client.js. This function reads the form values and fires an asynchronous fetch get request to fruits A or personal with a queue limit and boost checked as URL parameters. While waiting, there is a searching message that appears, which is probably too fast for you to catch it for this example. And then once the JSON response comes back, we loop through the result array, build cards using template literals, and then inject them straight into the DOM. So now if we look at these cards, each card shows the page title as a clickable link. So we can try custom title 27 or N-43. And then each also has the clickable link underneath, the search score to 4 decimal places, the page rank to 4 decimal places as well. And clicking view data loads the detail view, which is a fetch to the page. And this returns a full incoming and outgoing link list in scrollable panels with the count badges. So we have 30 incoming links showing the 30 badge, and we have 18 outgoing links showing the 18 badge. Underneath, we have a word frequency table of the top 30 words. And lastly, we have the back button that returns you wherever tab you came from. One thing that is worth noting is that all the text from the server goes through an ESC HTML helper function before being written to the DOM, so that a malicious page title can't inject HTML or JavaScript into the UI. Now, if we switch over to the personal search and then search a async callback and click search, for the personal site, we picked the Node.js site, which is nodejs.org. We picked it because it's large, it's well structured, and the API docs, guides, and blog all cross-link heavily, which makes it a good fit for PageRank, since pages that are genuinely important tend to get linked to from a lot of other pages. Quick notes on our page count is that our database has around 4,000 records total, but we only actually crawled 616 pages. The other 3,400 are just empty placeholders. So when the crawler finds an outgoing link to a new URL, MongoDB creates a stub for it immediately so we can track incoming links for PageRank. But those stubs are never actually fetched. They're just graph bookkeeping. So 616 real pages, which is above the 500 minimum and under the 2,500 cap. And then to add to what Trista mentioned on scalability, one specific improvement I'd highlight, let me just, oh, so yeah, it's loading. Anyways, one specific improvement that I'd highlight is the scoring model. So right now it's pure term frequency, which means common words like function or callback score high. Like these kind of words would score high on almost every Node.js page. And this makes the result kind of hard to differentiate. So TD-IDF weighting could fix this, by penalizing words that appear across many pages. Stemming and stop word removal would also clean up the noise quite a lot. And then those three changes alone would meaningfully improve result quality. And I think that is it for our demo presentation. Thank you so much for watching.